On average, every person will experience 2 broken bones in their lifetime. While current rigid implants, such as plates and screws, are able to heal many fractures, up to 18% still go to non-union, in which the bone fails to heal properly. I'm Connor Huxman, PhD candidate in mechanical engineering, and this is an overview of my research here at Penn State. I've been designing flexible orthopedic implants for improved bone healing, primarily looking at long bone fractures such as the humerus, but also looking at fractures of the patella or kneecap bone. So my research really lies at the intersection of 2 domains: orthopedic implants, specifically fracture fixation devices like plates, nails, screws, things used to surgically repair fractures, and then compliant mechanisms, devices that get their motion through elastic deflection, so things that are designed to bend or otherwise deform. And I've really tried to apply mechanical compliance to help accelerate both of the major mechanisms by which bones can heal. For primary bone healing, where compression between bone fragments is required, I've looked at pre-tensioning or stretching devices that can then deliver this compression as they attempt to return to their resting state. And for secondary healing, where micromotion is required, we can leverage the durability of compliant mechanisms to deliver repeated cyclic motion between bone fragments. Typically, the location and type of fracture dictate which mode of healing is preferred. The aims of my research are really spread across these 5 pillars, so it's very translational, starting with understanding the fundamental bone healing research, doing concept development. This is really the fun part, coming up with new ideas and designs. Then lots of modeling, both analytical to rapidly predict performance of flexible elements, but also computational with finite element analysis to predict more complex loading scenarios with implant-bone interactions. And then finally, experimental testing in surrogate or synthetic bone. My main focus has involved designing flexible, long bone fracture fixation plates to promote faster, stronger, and more reliable secondary bone healing. So this is a single-piece stainless steel implant with flexible members that elastically deflect by prescribed amounts known to be conducive to bone healing. So we're really incorporating compliance into the plate itself without changing the shape, material, surgical technique, or locking screw technology. In the last year, I've really been able to focus more on experimental testing, actually putting these designs to the test. So we were able to machine several different production quality compliant plates and test them in an established benchtop model. This involves drilling holes in synthetic surrogate bone, creating an osteotomy or simulated fracture, securing the plate to the synthetic bone with commercial locking screws, torquing them to spec according to surgical technique, and then fixing the bone in a mechanical testing machine with custom fixtures. So this gives us a repeatable, non-load-bearing fracture model that we can test. Testing results show that compared to rigid plates, compliant plates can reduce the stiffness into the range known to be conducive to bone healing and can also provide more symmetrical micromotion across the fracture site. While we typically see a reduction in strength compared to a fully rigid plate, all the compliant designs have shown no signs of failure after 100,000 cycles at half body weight axial load. So this is a pretty intensive load to experience during the healing phase in the humerus. I've also looked at fractures in some other anatomies on the side, such as the patella. So when you extend your knee, the patella experiences very large tensile loads, which can cause distraction at the anterior cortex or the front of the kneecap. So this is still in its early stages, but here I'm targeting primary healing with an initially undersized device that gets pulled into tension around the patella, secured with lag screws proximally, and can deliver that compression. This work has involved iterative simulations of various compliant arrays, and the results in an anatomical fracture simulation show that the proposed designs can increase total compression and concentrate that compression anteriorly when compared to a current treatment technique. So you can see how compliance can be leveraged for bone healing all around the body. And you can also see how this is a very multidisciplinary space. And I've been able to work with a great team of advisors in engineering design, orthopedic biomechanics, and also with surgeons who have clinical insight from treating these fractures. I also want to acknowledge Zach Coronius for assistance with mechanical testing, Bill Gannett and Ellis Dunkelbarger for machining expertise, and then all these people who have helped me navigate the entrepreneurial journey with this technology: Jeffrey Brandt, Nuwan Kapu, Erica Swift, Kevin Harder, as well as Allison Martinez, Suzanne Kajowski, and Jim Pietropalo. I've also received very generous funding from the Diefender for Entrepreneurial Fellowship, so I'm very thankful for all this support.